My name is Manishet Nilavong from Rubber Technology Research Center, Mahidol University. And today I would like to present my research work entitled Laws of Coagent Hybrid Ratios on Properties of Silica Field HNBR, modified with TESPT and VTEO Silanes. So let's start. Okay. So first, let's begin with introduction part. Firstly, I would like to briefly explain about the raw material used in this study, the HNBR. HNBR, or hydrogenated nitrile rubber, is a derivative of nitrile rubber. This kind of rubber can be prepared by the hydrogenation process of the NBR. And this results in the more saturated structure. And therefore, HNBR possesses many advantages. For example, excellent oil and nonpolar solvent resistance, high mechanical strength, and high thermal resistance. And therefore, HNBR is usually utilized for the production of O-ring, rubber roll, and tubes. In order to improve the mechanical properties of HNBR, the use of the reinforcing fillers are usually utilized. For example, the common black and silica. And in the case of the rubber product with a non-black color, the precipitated silica is usually used. However, as a result of the highly hydrophilicity of the silica particles, the use of silica usually leads to the poor dispersion of the filler in the rubber compound. And therefore, the use of the chemicals called silane clumping agent is usually utilized in the compounding process. As you can see in this slide, by the use of silane clumping agent, the dispersion of the filler in the rubber matrix can be improved. And it can be said that by the use of the silane clumping agent, the state of mix of the compound can be improved. And not only the state of mix, but the rubber and filler interaction can be improved by the use of silane clumping agent. As you can see in this slide, by the use of the silane coupling agent, the adhesion between the silica particle and the polymer matrix can be improved. So, the use of silane coupling agents can use to improve both the dispersion and the rubber to filler interaction at the same time. And moreover, in order to produce the rubber product, not only the filler, not only the silane coupling agent, but the curing agent is also utilized. And this work will focus mainly on the use of peroxide curing process. And in order to enhance the properties of the peroxide cure rubber, the coagent is usually utilized. And what is the coagent? The coagent is a kind of multifunctional monomer which is capable of reacting with the free radical from the peroxide. And many segments can be formed by the use of the coagent. For example, the coagent alone can be produced. The segment of the coagent cross-link with the rubber. And the segment of the many functional coagent in the same region, in the same segment right here. This depends on the types and the reactivity of the coagents used in curing process. And by the use of the coagent, the mechanical properties of the rubber and the cure efficiencies can be improved. And by the use of the coagent with various types, the various bonding can be formed. For example, the covalent bond and the ionic bond. In the case of the ionic bond, it can behave just like the sulfidic linkage, which is more flexible compared with the covalent bond. So, the advantages of the ionic bond composed of the high flexibility comparable to the polysulfidic linkage, together with the improved mechanical properties. For example, the tensile strength and the flex resistance. So, this work will mainly focus on two chemicals, including the silane coupling agent and the coagent. The first objective is to investigate the silane type effect, including TESPT and VTEO, on the cross-link efficiency and properties of peroxide cured HNBR. The next one is to study the coagent hybrid ratio effect, including TRIM and CDA, on cross-link efficiency and properties of peroxide cured HNBR. In other words, it can be said that this work will focus on the synergistic effect by the use of coagent and the silane coupling agent. So let's come to the experimental. The compounding materials is shown in this table. HNBR is used as the raw material, the raw rubber. Precipitated silica was used as the reinforcing filler and kept constant at 40 pHr. And the silane coupling agents used in this study include TESPT silane and VTEO silane. Both types of coagent were kept constant at 4% by weight of precipitated silica. The TMQ was used as the antioxidant, and the coagents used in this study are TRIM, trimethylpropane trimethacrylate, and zinc dicrylate, or CDA. And the ratio of the coagent will vary in this study. The DCP was used as the curing agent and kept constant at 2 pHr. The chemical structure of the silane coupling agent are shown in this slide. The TSPT silane composed of the 4 atoms of sulfur, while the VTO composed of the vinyl group in this segment. And the chemical structures of the coagents are shown in this slide. The trimethylpropane trimethacrylate, or TRIM, composed of 3 reactive vinyl groups, and the CDA, the zinc dicrylate, is reacting as the ionic crosslink. For the mixing procedure, firstly, HNBR was introduced, followed by the TMQ, zinc oxide, and stearic acid. After that, the precipitated silica, together with the silane coupling agent, was introduced. It must be noted that for the TSPT modified system, the discharge temperature of 140 degrees Celsius and mixing time of 30 minutes were utilized. And in the case of the VTEO modified system, the discharge temperature of 140 degrees Celsius and mixing time of 20 minutes were used. And after that, The compound received from the first step was introduced by the coagent, the trim, and CDA. And for the characterization, the swelling test was utilized in order to investigate the magnitude of the crosslink or the crosslink density. The crosslink density was measured under usual condition and under ammonia atmosphere. It is known that the measurement of the swelling test under the ammonia atmosphere is capable of breaking down the network of the the measurement of the swelling test under the ammonia atmosphere is capable of breaking down the ionic crosslink. So, by the use of the calculation of the difference between crosslink density obtained from usual condition and ammonia condition, the content of the ionic crosslink can be observed. And the rheological test was performed by the use of RPA 2000. And then the mechanical properties was measured by the use of the tensile test. So let's come to the results and discussion. The first result to be presented is the crosslink density. Firstly, please take a look at the result represented by the blue dot. This result was obtained by the use of the usual condition. And it can be seen that with increasing ratio of the CDA, the crosslink density increased. However, by the use of the swelling test under ammonia atmosphere, it can be seen that the crosslink density decreased as a function of the CDA. This can be proved that the ionic crosslink is already formed in the vulcanized. So, it can be concluded that with the increase in CDA content, the ionic crosslink also increased. This slide shows the crosslink density of the TESPT modified system. And it can be seen that the crosslink density obtained here is lower than the control system without the silent coupling agent. So it can be said that with the presence of the TSPT silane, the crosslink density of the vulcanized obtained from the peroxide curing is decreased. It is because of the cure retardation behavior caused by the sulfur atom released from the silent coupling agent. Under high temperature, for example, the curing temperature, this sulfur can be break down to the free sulfur. And this sulfur can behave just like a free radical scavenger and reduce the reactivity of the free radical. Okay. This slide shows the results of the VTEO modified system. It can be seen that in the case of the VTO modified system, the trim-rich compound shows the highest magnitude of the crosslink density. So, can be seen that with the increase of the trim, the crosslink density also increased in the case of VTO modified system. If we take a look at the chemical structure of VTO silane, the vinyl group is quite reactive to the free radical. So that's why the trim is also reactive to the free radical, and this makes the peroxide curing more efficient in the presence of the trim coagent. And this slide shows the comparison of the cross-link density, as you already saw here. The system modified with the VTEO silane has the highest cross-link density in the system with trim ratio, with the highest at 16 pHr. And by a comparison of the ionic cross-link content, it can be seen that with the use of the silane coupling agent, both TSPT and VTEO, the content of ionic cross-link seems to be decreased. But it doesn't mean that the CDA is less effective in the system with silane coupling agent. But usually, the ammonia atmosphere does not break down only the ionic cross-link, but the filler-filler interaction between silica also break down under the ammonia atmosphere and leads to the breakage. So this slide shows the results of the rheological properties of the vulcanizers as a function of strain. In general, if the higher magnitude of strain is applied to the rubber molecules, the energy dissipation is occur, and this represents with the increase in the tan delta magnitude. In this case, it can be seen that in the control system without silane, the system with the highest magnitude of trim shows the highest magnitude of tan delta also. By considering the chemical structure of trim coagent, the trim coagent contains of the carbonyl group, which is believed to be able to react with the silica particles. And that's why, with the increased loading of trim coagent, the transient network between coagent and silica also increased, and this leads to an increased magnitude of the tan delta. And this slide shows the results of the TSPT modified system. And compared with the control system, this system shows much lower tan delta magnitude. So it can be concluded that with the use of the TSPT silane, the extent of coupling reaction is responsible for the elastic contribution, which leads to a decrease in the tan delta magnitude. And this slide shows the results of the VTEO modified system. The high magnitude of the tan delta tell us about the lower efficiency to decrease or to coupling with the silica particle compared with the TSPT silane. But at the high strain region, the plateau of the tan delta can be observed. And this means that by the use of the silica surface treatment of the VTO silane, the transient network can be decreased. At the same time, as we can see that from the cross-link density result, the co-crossing ability is responsible for the threshold region of the tan delta right here. So This slide shows the tensile strength results of the vulcanizers. And it can be seen that the system modified with TESPT silane shows the highest magnitude of the tensile strength. And the elongation at break results shows the lower magnitude of the elongation at break. This means that with increasing the ratio of the CDA, the cross-link density increase, and this leads to the decrease in elongation at break. And the results of the M100 or the modulus at 100% strain. The VTEO modified system shows the highest magnitude in the compound with highest ratio of trim coagent. This is due to the cross-linking ability of the trim coagent, which can perform very well in the system modified with VTO coagent. And so, from the results, it can be concluded that the CDA-rich system is more appropriate with TSPT modified compounds due to its less influence of the Kiel retardation phenomenon. Moreover, the trim-rich system is more suitable with VTO modified compounds due to its ability to co-cross-link in peroxide curing system. And lastly, I would like to thank Associate Professor Dr. Chakrit Singh, who was my advisor, the Rubber Technology Research Center, or RTEC, and the Chemical Innovation Company Limited for supplying the chemicals. And thank you for your kind attention.